All right. Hey, everybody. Happy Thursday. Jumping into your kind of final little section, little lesson that you have for our little factoring unit, where really you just pick up a shortcut for some particular scenarios. And these scenarios are important to keep your eye on in Algebra 2 and beyond, where you're really going to learn them and really going to practice them a lot. Really just gets introduced here in Algebra 1. So what I'm going to do is I'm going to go through problem 847, 849, and get you to the perfect square, right? Perfect square trinomial shortcut, and then also the difference of squares, shortcut. And that's what we're going to watch in this video. Problem 847, it says special quadratic expressions like this, 9x squared minus 100 and part f of problem 846 can be factored quickly once you discover the pattern. And that pattern is called the difference of squares shortcut. But why do patterns like you found in problem 845 work, okay? All right, so what we're looking at here is actually problem 845. It was broken out onto the Jamboard, not on the Jamboard, on the Desmos earlier in class. My alarm's going off here, sorry about that. And here are actually the four groups that you set up here, right? That you set up in class. So let's take a look at this ones here. Okay, remember group number one right here, we found no pattern in the general. You could factor this one, you could factor that one. They're factorable, right? But with this one here, for instance, x squared plus 2x minus 24, this would factor to x plus 6 times by x minus 4. Okay, so nothing really particularly interesting about that. X plus 6 and x minus 4, those are two different factors. There's a 6 here, there's a negative 4 there. They're not really related. Once you got to this, in situation number 2, you got to an interesting pattern. Okay, you got to something called perfect square trinomials. And if we look at this here, look at these things that these things have in common, right? Have in common here. This is a particular pattern, right, that we lumped together. And people suggested this. I think these were the first two that people suggested bringing together. I think Elvis maybe suggested these two. But x squared minus 10x plus 25, that factored is something interesting. It factored into a repeated factor, x minus 5 times x minus 5. Okay, why? Well, what do we notice here? We see an x squared in front. Well, that's the x, and also has the x later. We also see a 25 at the end. Okay, how does that relate to negative 5? Right? How's 25 related to negative 5? Let me think about that for a second. We have a negative 10 in the middle. Interesting. All right, this one here, a perfect square trinomial. Well, what's going on here, and I think Graham kind of mentioned this towards the end of class, was that the last term here is a perfect square, something called a perfect square, right? This is 5 squared or negative 5 squared. This is 3 squared or negative 3 squared, right? One or the other. This is 2 squared, right? Or negative 2 squared is 4. So your front term here is technically also a perfect square. Look at this. This is 9. What do we know about 9? Well, 9 is 3 times 3. 4, well, that is 2 times 2, okay? So the hard part about this one, about actually using this shortcut, is that all of these are trinomials, right? These are perfect square trinomials, right? We have a middle term, and that's sort of the question mark. Where does that middle term come from? Why exactly does this work for perfect square trinomials? So that was one pattern. Here was the other pattern that we found. Which I think Theodore near the end of class suggested here, but we have difference of squares is the other pattern that we noticed. Well, we actually have binomials like this. Check this out here. So 4x squared minus 25, you should have gotten this. Should have factored to 2x minus 5. And then the factor is very similar here, except it's not minus 5. It's the opposite of that. It's plus 5 here. So 2x minus 5 times 2x plus 5. Now, these are very similar to perfect square trinomials, except look at it here. We are subtracting. Okay, always subtracting the x, the c term, right? The last thing that we have here. So what this is, difference of squares, is technically this is a square in front of us here. 4 is a square, right? Because 4 it could be made of as 2 times 2, right? And that's a square, right? Because a square has 4 equal sides. So if we're doing 2 times 2, we find an area of 4. So that's a perfect square. X squared is a perfect square because it x times x, right? Gives you an x squared. 9x squared is 3x times 3x, right? There we go, 3x times 3x gives you the 9x squared. And then the 1 here comes from negative 1 times plus 1. The 49 here comes from negative 7 times positive 7, okay? So then the question is here, what we have to do again, right? Similar to the perfect square trinomials one, where did this middle term come from in the perfect square trinomials? So the difference of the square problem is, well, why is there no middle term? Why is there no x term here? There's an x squared term and there's a 25. There's a numbers term or a constant term. There's no x term. There's no x term here. There's no x term here. So where did all the x's go? And problem A is going to have you think about that. Where exactly did these x's go when they're written up in this format here? Okay, because the goal of this is you want to find, right, if you happen to notice something, problem 925, maybe we should read through this question together. Sorry, this is 824 here. Let's read through this question together. But you want to notice something that's written in this particular format, okay, this particular format. You want to keep an eye out for that because you can actually factor these really quickly. And we're going to see too. I'm going to do this at the very ends, right? We'll factor some of these super quickly once I get done with sort of this mini lesson. Okay, part A, it says a quadratic expression in the form a squared x squared minus b squared is something called a difference of squares. Okay, why is it a difference of squares? Because we're subtracting one square, right? So the coefficients all here are all squares, a squared, and then x times x squared minus, and we're subtracting another perfect square from it, right? Difference, right? Difference means subtract, right? Difference of just squares, okay? What we're talking about is two squares. Difference of two squares. There we go. We can factor something really quickly. 8 factors to this pattern, right? A factor times by the same factor, you just flip the signs of the second one, okay? And this works out, and I'll prove to you that this works out right now, right? That if we have something in this format here where we notice a perfect square in front as our first term, and then a perfect square getting subtracted from it as our second term, we can actually write our factors as this, as the square root of the first term plus the square root of that second term right there, right? Even though this is negative here, I'm gonna go plus b, and then times by the square root of this front term here, right? Where you just took the square root of this. Here we get ax minus the negative square root of this, right? So minus b, okay? This here, these sort of opposite, not really opposite factors. I mean, the signs are different here, but they are equivalent to this perfect square binomial, right? Not perfect, sorry, difference of squares standard form, right? The binomial we have here, because check it out. Let's actually prove it to you that this has to equal this. So we're going to start with this as a product, and I'm going to prove to you that this is going to be its sum. Here's how it's done. Ax times ax, well, a times a is a squared, x times x is x squared, okay? Negative b times positive b, right? Negative b times positive, well, b times b is b squared. If I'm multiplying a negative to a positive, I gotta make that negative, okay? Check it out here. So I have this. I have a squared, x squared, minus b squared, okay? That's actually what my sum is then gonna end up being. So then the question is, what happened to the x's, right? Normally I have x's here, okay? Normally I have x's here. But what happened to all the x's here? Because if I do this out, right? If I'm trying to figure out like how many x's I have here and how many x's I have here using this generic rectangle, I got to do this. Ax times by negative b, okay, so this is going to end up being negative because we have a negative times a positive. That would be negative bax, right? Negative b times ax is just negative bax. Here, oh, what goes in this corner? B times by x, and positive, right? It's all positive. We don't need negative signs. Here I have b times by a times x, okay? So what do you notice here, right? This is just a generic kind of difference of squares factored thing. If I multiplied it together, what happened to my x's? Well, if we pull our sum out here, right? So I'm talking about the insides. I'm going to pull the sum out here, a squared, x squared, and I'm pulling out these guys right here. These are just going to cancel out, which I'm hoping you see, right? Negative bax, well, that's just the opposite of bax here. So they end up canceling it out, right? Canceling out. The diagonals here, because this factor here is that opposite sign here, and then this opposite sign here, we're going to have a negative, right? Negative final term, right? When we subtract it from the original, that's why it's a difference of squares. And then we're not going to have to worry about a middle term at all because they'd cancel out, right? They cancel out. This is the same value, right? Same value multiplied to the same value, except one of them's negative, so they cancel each other out here. Okay, so just to prove to you, this here, that factor times that factor, right? So ax minus b times by ax plus b, it equals, well, what we see up top here, right? I should just prove to you by multiplying using a generic rectangle. A squared, x squared, minus b squared, okay? So your head might be spinning right now, and that's okay. This is just an introduction to this. You don't even know this stuff super well. You don't even know this stuff for Friday either. I just want you to factor things quickly if possible. We're going to talk about the perfect square trinomials because this is another thing that works here. This particular format right here, it's something called a perfect square trinomial. So let's maybe take a look at it in a second and maybe compare to what we have up here for some of our perfect squares. Okay, this is saying here a perfect square trinomial. Again, there are three terms, right? Three terms right here. One is a perfect square at the beginning. Okay, check that. This checks the box of that. 4x squared, cool. 2x is the square root of that. Square root of 9x squared is 3x. Okay, the middle term is twice, twice times whatever the square root of the front is. So twice 2 times by whatever the square root is back here. So twice 2, so that'd be 4. Square root of this is 5. 4 times 5 is 20. This is a little tricky, right? A little tricky here. So square root of x squared is x. Square root of 9 is 3, or negative 3, right? It could be negative 3 too, because negative 3 times negative 3 is 9. This is twice that, right? This is twice that, okay? So here's actually the thing to look out for, right? Here is that middle term being 2 times as much as the square root of the first term times the square root of the last term. That's the thing to look out for. It's a little bit hard. It takes practice, though, right? It takes practice. That's why it's just getting introduced to you here. So let's just show you why that is, right? It might jump out to you if we actually take this and multiply together, and I'll show you why the middle term is twice the square root of the first term and the last term, right? And just something that kind of comes up here. So let's check it out here. If I had this is a perfect square, right? Because check it out here. This is a perfect square, right? Because our base equals height, okay? Right? This is the same, okay? This is a square because the base equals the height, right? We have the same, we set up a generic rectangle with our width is ax plus b and our height is ax plus b. It's the same exact thing. So if it's a rectangle with the same width, the same height, technically a square is a rectangle that has all sides that are equal to one another. So it's a square, right, when it comes down to it. So if we distributed this, right, if we multiply this here, if we find our sum, multiply together, our first term of this, right, so if I'm doing this here, maybe I'll just do it together here. If I'm trying to do this to prove that these are the same, I would do ax plus b times by ax plus b. And if I did that, I would get, well, a times a is a squared, x times x is x squared. So I would get this, a squared, x squared. And then this term up top here would be b. And again, these are just like variables to represent things about, like if we had these were numbers, it would work out this way. It's just supposed to represent kind of numbers that would be our coefficients in this situation, right? So we have, this might be 2x plus 5 times 2x plus 5, and you'd have to multiply the 5 by 2 to get this one up here. So this is BAX up here. What's going to be down here? Well, this is going to be BAX as well. So because we have B times by AX. So it's going to be the same thing. It's going to be the same freaking thing right on the side here. That's why we have this pattern. That's why we have this thing in the middle here, which is twice as much whatever this is times whatever this is here, right? Like, because you have to do that twice, right? You have to multiply this by that once, and then, this by that once, and then we got to do this by that again. And we're going to end up with plus 2. They put ABX, that's fine, right? Ordering doesn't matter when you're multiplying, so I'll do it that way. 2ABX, okay, plus, finally, B times B. What's B times B? That's B squared, plus B squared, okay? So this is a perfect square shortcut, and really the thing to look out for here is that the first term is a perfect square, the last term is a perfect square, and maybe, right, once you realize the first term is a perfect square, the last term is a perfect square, maybe you can get the middle term to kind of make sense and realize it's a perfect square and you can factor this really quickly, okay? So just to quickly, I know this is kind of overwhelming. I'm going to put the factoring shortcuts right here for you to potentially put in your notes. And I'm getting rid of the x here. I don't think I need to like have this x here. The x thing here makes it look a little bit more scary, a little more confusing. So this is what I would put in your notes, okay? Pause the video and maybe spend like 2 minutes writing this in and really thinking about it, right? Really thinking about why these statements here are actually true, okay? Pause the video, factoring shortcuts, put in your notes, put this in your note, put that in your note, because these are the 2 shortcuts you got to do. Ready, set, go. Pause and write it down. Has it been 2 minutes? Have you spent 2 minutes with this? I hope you have, okay? So the things you've copied down here, maybe thought about, this first one here, a squared plus 2ab plus c squared. This is sort of another textbook, right, would show it this way. A lot of textbooks show it this way. This would tell you that this is a perfect Square what? Square what? How many terms are there? 3, right? Perfect square trinomial. So when you notice something in maybe this format right here, in your homework, your very first problem, they're going to give you a couple that are actually special, like this perfect square trinomial is here. Like, check this out here. What's the square root of 4? It's 2. What's the square root of x squared? It's x. So 2x. What's the square root of 1? It's 1. So 2x times by 1 would be 2x. Double it, middle term, cool. I can actually factor that right away. And we can get it done real quick. Check it out here, because this is going to be 2x plus 1 squared. I'm done. I'm done. Reason why that is true, again, right? If I did this, if I actually wanted to check it out in my head, I did 2x plus 1 times by 2x plus 1, I would get 4x squared here. I would get 2x up here. I would get 2x down here. I get 1 times 1 is 1. And look at that, right? This diagonal here delivers me that 4x that's in the middle, because I had to multiply this times that once. And I had to do that twice, not just once, twice, right? Twice here, okay? So that's perfect square trinomial shortcut. So if you happen to notice this, right, you don't have to do it this way, okay? You didn't have to do it this way in class. You were able to get all up through A through K, I think it was, factored using diamond and rectangle. And perhaps it took you maybe a little longer than other people, but other people, there were, I don't think anyone really knew these shortcuts before this, but you can do this still with a generic rectangle and a diamond like we always have. But if you notice this, you can do it faster, right? Faster. And sometimes mathematicians just want to do stuff faster and get through it. And I think even our 10th graders, 11th graders, 12th graders, right? People in the higher level math classes want to do things faster. So keep an eye out for this. First term's a perfect square, right? X squared, 9x squared, 16x squared, right? Because 16, the square root of that before, 25x squared. Last term is a perfect square, 49, right? 7 times 7, or negative 7 times negative 7. So this could be negative, right? It could be 2. So if this were like x squared plus 14, x squared minus 14x plus 7, that's a perfect square. Plus 49, that's a perfect square, right? Because square root of 49 is 7, or negative 7 times by x, which would be the square root of x, would be negative 7x times 2 would be negative 14. So anyway, sorry, I'm saying a lot off the top of my head, kind of getting here. All right, some ways you'd see the perfect square trinomials is this is going to factor to a plus c times by a plus c. Okay, that's how we got this one here, right? Remember, this is a squared, okay? A times a is a squared, okay? C times c is c squared. The thing that you forget is like why this is 2ab right here. Well, that's just because we do c times c. If we did a times c over here, oops, and we did c times by a right here, you'd have to do c times a and then another c times a. So it would be 2 plus 2ca. Okay, just showing you another way that they connect. They're the same thing here, okay? Here's how I'd write this out, though. Right, I'd write that out. Now, like this here, because a plus c, and then doing that again times itself. Simpler, right? Simpler to write down as a plus c squared, right? 2 times. A plus c times a plus c is the same thing as a plus c squared. So that's typically how I'd write this down, and that's why I wrote this as my answer here for C. Okay, there's one shortcut. Here's the other one. Perfect square, this difference of squares is this one. Okay, you're either a perfect square trinomial, you have 3 terms, or you're a factorable shortcut, which is a difference of squares. I want to call this one out too, because this shortcut doesn't apply to this guy right here. Okay, remember this one right here. This is x squared plus 4. That's actually something called a sum of squares, and that is not factorable. Hopefully you saw that today in today's class, that you can't factor that guy. You can't make that into a rectangle. If you have an x squared here and you have 4 ones, you need to have some positive x's to fit in there, right? But you don't have any positive x's, so you can't actually factor that one. Difference of squares, you have one term is going to have positive, the other term is going to have negative for what you're going to have to multiply by x eventually. So it's a little bit confusing here. Okay, a squared minus b squared. Okay, so check out this one here. What's my a? My a is x, right? Square root of this is square root of this is a squared, right? So square root of this would be x. And square root of 64 is 8 or negative 8. So here, this factors really quickly. This is going to be x, okay, square root of that, and then the square root of 64 or negative 64. Well, negative 64 doesn't have a square root, but 64 has a square root. It's either positive 8 or it's negative 8. Okay, it's negative 8. Done, and we're done right there. Okay, the reason why this works, again, if I multiply it all together, x times x is x squared. 8 times negative 8 is negative 64. But remember, if I do 8 times x, that's 8x. Negative 8 times x, that cancels out, right? That cancels out. So plus 8x minus 8x. Okay, so those middle, the x's all cancel out, right? And then that would be here, okay? More shortcuts. You can practice with shortcuts. You get 849 part B. This is going to equal y minus 3 squared. How did I get that? Square root of y. Well, that's just y. Square root of 9 is 3 or negative 3. But if I do negative 3 times y, that's negative 3y. Double it, that's negative 6y. So there is a shortcut for that one as well, too. So you just got to keep an eye on when you actually see perfect squares as and you'll get better at perfect squares. We'll practice perfect squares more throughout high school. If you look and keep an eye out for perfect squares, you can sometimes find a shortcut. That's my takeaway out of this here. This one here, 5x squared, 5 isn't a perfect square. 45 is not a perfect square, but check it out. If you're going to factor this one completely, remember, you got to ask yourself, I have a 5 here. I have something that ends in a 5 here. What can I do? I can factor out a 5 of this one. So this one, we're going to use a shortcut in a second because I've done this problem before. If I factored out a 5, well, 5 times x squared is 5x squared. What times 5 is negative 45? Well, negative 9. Check it out. We have a difference of squares right here. So you have the difference of squares within this. We factor out the 5. It's the same thing. Factor out the 5 and then factor again if you can. And this is going to be 5 times by, well, this is a difference of squares, so I'm going to simply find the square root of that one. The square root of this one is just x. So x minus 3 times by x plus 3, right? And that's the reason why we have no middle term here for this expression, right? We just have x squared minus 9. It's a binomial, but it's quadratic. We're just missing the middle term, right? It's not the trinomial here. And there is our answer. Okay, so if you follow this here, like it's just mostly just want you to know these shortcuts exist, and then in time, right? Maybe start using them. Maybe you have to practice them in Algebra 2, but we're not going to spend a ton of time on them this year. Send me any questions if you have them. You don't need to know the shortcuts for the quiz necessarily, although you're welcome to use them if it saves you time and you want to flex that you know this. This is it, I guess. You only really have like 3 other problems other than this here. So thank you for watching. Let me know if you have any questions. Take care.